Welcome to the course on two-dimensional signal processing, principles and practices. We had done the 2D convolution through 1D convolution in the last lecture by knowing that the separability concept, which helps in finding out the 2D convolution of two sequences, or the one sequence which has to be convolved with the other one, same thing, in which the impulse response needs to be separable. So if impulse response is separable, for this case, if h of n1 comma n2 is separable, that means we will be able to write it in terms of product of two sequences, two 1D sequences. One index is 1 and this is 2. So if you are able to do that, then this particular system is separable, so that we can find the convolution of that to determine the input signal response, that is x of 2D, for any arbitrary input response with the use of impulse response. So if h of n1 comma n2 is this for 2D signal, are the impulse response of your 2D system. So 1, minus 3, 1, minus 3, 6, 9 and minus 3, 1, minus 3, 1. So if we take this matrix, can we separate it into h of n1 comma h of n2? So the sequence what is given over here, this 2D sequence, that is the impulse response, is separable or not. How do we find that? That is, it can be written in terms of 2, that is row vector or column vector, or we can find it like this is 1 minus 3, 1 can be common and take the rest of them as column vector, or minus 1, 3, minus 1. So in that way is 1, minus 3 and 1. Can we write it any one of this in this form? So if you find it, this could be similarly here 1, 1, 3 into 3, again this is going to be 9, and 1 into 1, 1. So the various ways in which this column vector can be obtained from this two vector combinations. This is not the only one option, just it has been given here to have the dependent rows and the dependent columns. Any one of this can be taken as one first, and then the row and column multiplication would result in the square matrix. So what similarly the example which we took also already similar to that, my 2 by 2 matrix, a square matrix, in which this can be written as minus 1, 1 is a common, these are dependent rows and columns we have here. So minus 1 and 1 into 1, 1. So this can be written into product of two sequences, the two matrices, row and column. So where h is equal to minus 1 into 1, 1 here, plus 1 into 1, 1. So this can also be separated this fashion. So what is the condition for which this separability can be done? So if you recall that in the previous lecture we had learned that it should be a square matrix, and then that there should be linearly dependent rows and columns in that, and then the determinant should be 0. If you compute the determinant of this dependent rows and column matrix, it will be 0, and it's a singular matrix. And if you have the n by n square matrix, the dimension is n by n, there are n minus 1 such solutions possible. It's not the unique solution here, so no unique solution for this, and it is not invertible because this determinant would become 0, so not non-invertible matrix. So the impulse response of 2D having all these properties, okay, so then that impulse response can be separable, and if the impulse response is separable, then the 2D sequence is separable, or if it is an impulse response of a system, then that system is having the separability concept. That is, we can use it, this separability concept can be extended to other analysis as well. Right now we are extending to convolution. So then if its impulse response, this 2D system's impulse response is separable, then we can use we can write the 2D convolution, or we can get it the 2D convolution through 1D convolution by making the column wise convolution first and then row wise convolution, or in the other way also, row wise and column wise, this can be reversed even. So it's possible to get the 2D convolution through 1D convolution. So now we would take up some of the codes what we had learned so far in MATLAB codes, and try to plot these 2D signals and 1D signals as well, and the 2D sequences and 1D sequences as well. the things which we had learned for convolution, how do you perform in this MATLAB code for 1D, and how do you perform this 2D convolutions as well. So just to as an elementary exercise, this is given as this x is suppose having the signal values 2, 1, -1, 0, 1, 4, 3, 7. So if this is the case, then time index, the discrete sequence time index is given as n1, 0, 1, 2, 3, 4, 5, 6, 7. So it's just a time index, and another time index n2, it's given -3, -2, -1, 0, 1, 2, 3, 4. So in this case, this can we plot this x with respect to n1 or plot this x with respect to n2? So that's what we are doing here. Figure, so figure would generate, I think those who are familiar with the MATLAB, then to generate a figure you can use this different figures, especially you can use the figure command, figure stem of n1 comma x. That means this n1, the index time index is starting from 0 to 7. So it should match anyway when you are plotting the number of elements in x and number of elements in y which against which you are plotting should be same in the case of, otherwise it would throw an error. So stem plot is used to do plot the discrete sequences. You would get the plot, it's not the plot which is used for continuous time sequence. It is a discrete time sequence. Is always preferable to have this in the stem format. That is we can visualize it now. What is the stem meaning? The other, when you write another figure here, it would pop up as a second figure window, that stem n2 comma x. So this x is again plotted with respect to another time index. So you can see the time index here, it is -3 to 4, and then here 0 to 7. So but ultimately both the time indices are matching with the x. So that is the mandate here. N1 x vector length should be same, n2 and x vector length should be same. So if we take the plot of the first one, so we get this plot as n1 and this is x. So x is in terms of n1 here, just the index is shown as n1 here. So we have get 2, 1, you can see that -1, 0 and 1, 4, and this is at this one can 6, 3, and then it is going to be 7. So this is the plot of the first one, just a simple discrete time sequence. So you can see the stem which appears as this. Okay, this is the stem discrete time plot. We use it for the discrete sequences, especially in the MATLAB. So the markers can be used for increasing and decreasing the size, and in this case, so it would give just an unfilled circle. So you can fill it with that, with the commands like filled marker and so on. So this is a 1D sequence, discrete sequence. So if we plot the same with respect to another n2 and x, here the negative indices also possible to -3 to 4. So how do we plot this -3 to 4 here? So the time indices, and the only thing is the mandate, we have to match the vector size. So x of n2 gives you the same sequence with respect to the, if you notice this n2 is different, -3 to +4, whereas in the previous case it is 0 to 7. Now the getting the plot of this discrete impulse. So we have learned that signal models in 1D as well as in the continuous time and discrete time as well. So discrete time sequences will be used in this course. So we are just taken the examples of the discrete sequences. So one is this discrete impulse. How do we plot this discrete impulse in the, this is 1D again. So n is varying from -10 to +10. So the u are the delta, what we have, we can just framing the axes here. So zeros of 1 comma 10, and then 1, and zeros of 1 comma 10. So this 0 1 to 10, it would take zeros of this means at least 10 columns of one row. It makes 0. So zeros is a command. It would take 0 0 0 0, and then the center one is 1, and then it is zeros 1 comma 10. This again making it 0. So this is matching with the n and u. When you plot it again, you should be checking that stem is n comma u here. The zeros, this is from -10 to -1, and then 0. At 0 this would be 1, and then plus 1 to 10, this would be again 0. So if you take the plot of it, -10 to 1, this circle would, the stem would give the zeros, and then at 0 it is 1, and it is 0, 1 to 10, it becomes 0. So this is one way of plotting. You can do it in many ways, that we just show the MATLAB discrete impulse plot, how to get it in this. So the stem command is used for the discrete uh, signal plotting. And then discrete step sequence. So if you take the step sequence, so you have made the code as a generalized one. You can always have this in different fashion. So it's just to introduce a function x comma n. So this function which has the x value and n value as outputs here. So step sequence n0, n1 and n2. So these are the input to the function. So the parameters are passed to this function, and where n is taking n1 to n2, whatever the n1 n2 values are given, suppose minus 10 to plus 10. So this would vary from you can notice the colon in between n1 to n2, this n is varying, and the x is now we have to find out what is x. So it's a step sequence, so that we know that x is going to be greater than or equal to 0 of n indices, it is going to be 1. So x equal to n minus n naught, or simply forget this n naught right now, n greater than or equal to 0. So this value is going to be assuming x for 1. If this condition is true, then x will be 1. If not, x would be 0. And stem n comma x end. So if n naught is 0, suppose n here minus 10 greater than or equal to 0. No, it will be 0. And if n is 1, then it is greater than or equal to 0. So this value become true. So x will assume 1. If you can introduce that, you can stop this step sequence from any n naught. It is not only for 0. This is given only. It can be, suppose n naught is 2, and from 2 can we shift this step sequence. So that's how this is modified, this n to start this unit step sequence at any value of n naught. So here n naught is assumed to be 0 and n1 is minus 10, that is minus 10 to n2 is plus 10. Minus 10 to plus 10, we would plot it for this step sequence. So we get this plot has minus 10 to plus 10, that is n, what we had n1 to n2 values have been taken, and you can see for these conditions this x is yielding 0, minus 10 to 1, and from 0 to 10 you get this condition would be true, so it gives 1. So that is plotted in using the stem n comma x. N is varying from minus 10 to plus 10. So this is to obtain the step sequence. As n naught varies, this can be shifted right also or left as well. So then discrete signal, let's take a discrete signal and plot them and then shift it, the shifting which we have done in the previous step sequence as well. It is introduced. So the function y here, y comma n, this is y comma n equal to shift x comma m comma k. So in this, n and y will be taken as an output here. Okay, so yeah, and the inputs of this is x and m and k. So we have to give this n as n equal to 0 to n, 0 to 10. Okay, so what is x? We need to, so here sine 2 pi 1 by 10 star n here. So the value which you so this is for the different things that we can do it, get the outputs. So here, so the figure which on stem n comma x, if you simply use this alone, so we're forgetting about this the function inputs. So stem n comma x, if n is varying from 0 to 10 here, there will be 11 points, and sine 2 pi 1 by 10 n. So for 0, n is varying from 0 to 10, it would calculate the sine values and just plot this stem n comma x here. So you can get this x of n as this. So simply this code with this. So instead of having the function, so n comma x is this, n is given and then x of n is plotted over here. Now what is the resultant of this function signal shift? So can we shift this function, that is going to be y of n is x of n minus k. So if we shift it right or shift it left, so anyways this can be done depending on k plus or minus. So now we take the sequence in which k is minus 2. Okay, so k, make it minus 2, that, and m is whatever the m is equal to n plus k. Can give this n shifting the indices which are designed n plus k, then y, assume that y is equal to x. Okay, so this m value, and you can calculate this sequence, this x with that m, what is n plus k, what has been given here, and then plot this stem with respect to m comma y. So we can use this piece of code in that and then change the index to m, and the y of m is going to be the plus 2. Here k is minus 2, so n times minus k, what we get is this plotting from minus to 0. So you can see this sequence which is not starting from 0, it is starting from minus 2. So this is the plot of the discrete signal shifted sequence, right side sequence. Right side it is shifted, and then we can have this one, or left side shifted, depends on k equal to minus 2 or plus 2. So we get x of n minus 2 or x of n minus 2 or x of n plus 2. This is going to be the left shift, and this is going to be the right shift, delayed sequence or the advanced sequence. So the figure command can be used to generate the different figure windows. So now, using how do we add these sequences, because we need to add this sequence and subtract them, and signal operations needs to be done. These are all for the one dimensional case we are looking at. So the function y comma n signal add x1 n1 x2 n2. So these are the inputs which x1 n1 and x2 n2 are required for this. That is, n1 is minus 2 and colon 5. So in this case, the n1 index is minus 2 to 5. It is varying, and x1 is computed, it is a sine wave, sine of 2 pi 1 by 5 into n1. So you can have this f as this 1 by 5, or you can look for 50 hertz sinusoidal signal and specifying its time. So write this equation in the continuous time domain, is it sine 2 pi ft, and then x of t suppose equal to sine of 2 pi ft in continuous domain. You can make this discrete by 2 pi f n ts, specify this ts value, and n varying from 0 to whatever the value required to be plotted. So this would be x of n. You can have this discretized version as well by having from the continuous one. So this straight away, this n is given, this n1 how much it needs to be varied, and this f and ts has been taken over here 1 by 5. So the figure stem n1 comma x1. So if you this is just plotting the sine sequence, and x2 is another sequence which is from 0 to 5. So the index you can see that this is not same as this. Okay, x2 is sine 2 pi 1 by 10 and n2. So these are two different sequences. This first one is this from minus 2 to 5, you get this sequence. Okay, so this is from x1, this is x1, x of n1 I had put, that is from this sequence, this is equal to x1. And then we get the second sequence, figure sum of n2 x2. So which is here n2 x2, which is from here the index 0 to 5. So you get the sequence as 0 to 5. This is x of n2. So up to this we have plotted the two sequences, and then to carry out the addition. So addition of these two sequences, and if you see the indexes of these two are not matching, that is 0 to 5, and that is from minus 2 to 5. So n1 is indices is minus 2 to 5, and whereas here 0 to 5, these two are not matching, this dimension is also not same. Okay, so to make it, when you add it, at least make this n1 and n2 same for the two sequences, and then add it together. So that means you need minus 0 to here minus 2, 1 and minus 1 and minus 2 should be having this value, or find the lengthiest sequence in this. So for that we need to have the n, the new one, minimum of n1 comma n2 to maximum of n1 n2. So find the maximum of this n1 n2 at that side, and from the minimum what is the value. So here, and that y1 0 of length n. So with this length you make this index 0, then assign this y1 to y2 here. So that's y2 will be we would see, what is the value here, y1 and y2 will be of here equal length, and then y1 of find n minimum and n maximum, assign x1 value, and y2 of this similarly find the minimum and maximum, assign this x2 value, and then add these y1 and y2. So that's just two sequences, so making the indices equal. So that's what we are doing through this process here, y1 and y2. So first making them all zeros, finding the minimum maximum and making the indexes 0 0, and then what is that for this index, assume x1, and here and y2 assume x2, So from minimum to maximum, so that it is equalized in this case, that then add these two sequences y1 plus y2. If you add as such, these indices are not matching, so simply without doing the previous process, this would yield 0. I mean it will throw an error, it won't give you the output y addition, that is y1 plus y2. Similarly, you can do the multiplication as well, y1 or y2, and figure stem n comma y add. So the added sequence is this, y add n of n is this sequence. Now you can see this is -2 to 5. So the first sequence was up to -2 to 5, second sequence was from 0 to 5. So the second, we equalized this indices, and what was assumed for y2 then? Okay, that is x2 is 0 in these values, right? So this should be assumed 0 in those one where the length is less, especially in the x2 or the y2 which we had taken, but adding this value would yield the two y1 and y2 gives this response. So we have to take care of the indices when we do perform the signal addition in 1D, as well as true for 2D. So now how to generate the noise sequences here? So the n, use a rand function. So this is distributed between 0 and 1. The rand function of this MATLAB, this whatever the value give 11 points, n is from 0 to 10. So 11 value 1 to 11, you will get the rand value, x1 equal to rand of 1n. So this is a built-in function, figure gives stem n comma x1. So this would just generate a value random from 0 to 1. Okay, so the value would be always 0 to 1. It would plot the 11 points. So the 11 points would be generated because n is 11, and the indices should be matched with this n equal to 11, 0 to 10, or that means 11 points, and these 11 points should be matched. So this is just a random value which is generated between 0 and 1. And you can also generate this Gaussian sequence with the x2 rand n function, that is using the rand n function, figure n comma x2 grid on. So here this would generate the value random sequence which has the mean 0 and variance 1. So that way, if you take those values and plot it, this is also generating the 11 points. The indices are 0 to 10. What we would do, get is the 0 mean, and the variance, if you calculate for this data which is generated, will be 1. So if you want to generate a sequence, random sequence with 0 mean and variance 1, you can use the rand n function. If it is simply between 0 and 1, that is, use the rand function. So this is to generate a 1D noise signal, can be generated and added with the signal, and then for testing, also designing the filter and testing it. So this can be used, that is 1D rand n functions. So for 2D, let's move on to the 2D function, that is 2D discrete exponential function. So here, if you recall that we have done this in the lectures, x of n1 comma n2 is equal to a power n1 and b power n2. A, b values are given as 0.5 and 1. So it's an exponential sequence, 2D exponential sequence. How do we plot this one? So use this for making the CLC clear and close all, and for the previous programs or anything is there, and to clear it. And then A is 5, declare them, B is 1, and n1, what is the way in which you are going to vary n1 and n2? So n2 can take minus infinity to plus infinity, any value. Here it is restricted to 0 to 5. You can always make it minus 5 to plus 5 or minus 10 to plus 10 and so on. n2 also similarly. And what is the sequence which is generated? If it is 0 0, then x of 0 0 will be 1, no? n1 0 a b. Simply, so this a and a is 0.5 and this b is 1. So it was going to be 1 1, and if it is n1 1 and n2 1, so you would get 0.5 into 1, this will be 0.5. So similarly, you can calculate this value. We have done this, and then we had made the 2D plot. So now in MATLAB, how do we get those plots here? n1 comma n2, there is a mesh grid which helps in finding out n1 and what is the n1 and n2. This would repeat that value 0 to decide the indices. Okay, so and then if you vary that x, this would calculate the power of this A value, matrix values. If we have n1 varying from 0 to 5, it would calculate, and b n2 also it would calculate from 0 to 5. So we can use this a of a power n1 and a power b power n2, and then use the figure stem 3 plot. n1 comma n2 comma x, which is filled with this. So stem 3, you can see this is a 3D stem. It's not a 2D version of it, that is for used for plotting 1D sequences. So we simply use stem, that is going to be used for plotting the 1D sequences. For 2D sequences and to visualize in 3D, so stem 3 is n1, n2 or and x. So these are the three things which we are plotting here with filled. So if we use that function, you would get the 3D plot, that is n1 varying from 0 to 5 and n2 varying from 0 to 5 as well here. This is just a plot which is shown. So n2 is also 5. So you can see that n1 0 and n2 0, this is the plot, and then n1 n2 is 1 and n1 is 0, this one, and similarly this one. You can see the exponential sequence. I have showed you in the lectures also, but here we are looking at how do we get this plot. So to get the using the stem 3, because of stem this you get this as a like a stem, and this marker and marker size, the colors and other things can be varied using the properties. Now the thing is, if you want to look at as a n1 versus n2 plot, like what we did in the lectures, n1 versus n2, and get these values like these plots. So to get only the plot without calculating this x1 and n2, you can use the plot n1 in the same code, plot n1 colon and comma plot n2 colon. So that would give them only the plot like that, but doesn't change the magnitude what is calculated here. So if you want to have this such type of plot in this, you can rotate this plot and to have this even like a plot like this. So if you try to rotate the 3D plot, which can have this plane of z which is reduced, so that you can get this type of plot n2 versus n1 that can be rotated. So this is the plot where we had normally see that these are the amplitude values of x and n1 and n2. So from this we take one more example of this 1D convolution. The sequence, now you can plot this sequence 0.7 power n u of n and 0.2 power n u of n. This is also a example which we had done already. Index you define it, and x and h, these are the two sequences, take them, and n is defined after 0, so there is no need to multiply it by u of n here. So convolve, simply convolve is the command used, CNOV x comma h. So now why you know the length will not be same as this x and h. If you recall that 1D convolution, that would have the length n1 plus n2 minus 1, right. So this is the first sequence length and n2 is the second sequence length. So the resultant sequence n equal to n1 plus n2 minus 1. So that's what we had done here. So 0 is here starting n, so we need to change the index to plot it, n comma y 0 colon length of y comma y minus 1. So y is obtained from here, the convolution length is this. So we have to change the index of n now, it's not 0 to 10. So it is 0 to n1 plus n2 minus 1. So plot stem n y, that is a new index comma y. So you can't plot it with respect to the y, the n as such. Okay, so this y needs to be plotted with the new ny, because when plotting you need to match the index x and y. So this n is from now 0 to 20, that is here we have 11 plus 11 here 0 to 10, right. So this one is 11, 22 minus 1, that is there are 21 points here. So that's what it is shown over here. So there are n1 is equal to 11 points and n2 equal to 11 points. So there are 22 points minus 1, 21 points, which is plotted for 0 to 20 in the case of convolved sequence. That is y is going to be between 0 to 20, 0 and 20. Now taking the next sequence, which is discrete 2D convolution via 1D convolution. So in this case, how do you perform this 2D convolution through 1D convolution? So x, the signal which is taken, the example which we had already solved in the lectures, 1, 2, 3, 4, 5, 6, 7, 8, if you take this matrix, and h is the impulse response. So impulse response is separable and is separated into h2 and h1, and the product of 2, 1, 1 and 1 minus 1. So we get, this is the first we are going to do the column wise convolution. So get the f of k1 comma n2. So k1 comma n2 is x of n1 comma n2, this one, and then convolve it with h of n2 first for column wise convolution, that is this one, h2, 1 minus 1. So use the convolution command here. So the first here, convolve x of colon comma k h2, so that is taking every column of the x. Okay, k is varying from 1 to cx, so this column is taken. So column would be computed from the length, and then find it, convolve x of colon comma k h2, that is the first one, and then do the row wise convolution, that is 1D convolution, every n2, that is this value, perform this f of k1 comma n2, what we have got, with the row wise convolution, that is the impulse response h1 of n1. So again we have to make the size row wise and column wise is size of f, that is depending on this size, and cy, that adjusting the length index is important, that cf plus length h1 minus 1. So you get the y as the zeros, how many rows we need, row indices size is used, and put that cy length. So you get this rf comma cy here, and display this x. The command is only convolution. So convolution x of k here, k is varying in column wise and h2, and then perform the same for the f into h1. Okay, so display this y. So we get the output as 1, 2, 3, 4, 5, 6 and 7, 8, 9, and h was 1, 1, minus 1 and minus 1. So this we have splitted into h1 and h2 and convolved with first column with h2 and then obtain results with h1. So we get the output as this, which we had done in the lecture as well. The rows and columns are shown here as a matrix. When we plotted, that was a 2D sequence. So the n1 and n2, the positions would change when you take the MATLAB coding here. That is in a matrix form. So matrix form, index is 0, 0, and this is 1, 0, 2, 0, and so on. So this would be 0, 1. So when we take out the signals 1, and so this is, if you just recall in the lecture, that is this row from starting from here, and it moves up over the n2. So the circular convolution, in which we have taken the two sequences x1 and x2, 2, 1, 2, 1, and x2 is 1, 2, 3, 4. So take the length is n equal to 4, which is known over here, or you can find the size of this sequence and put it over here. That's also, but the length should be equal. So the circular convolution, c convolve, the command used is c convolve, get y. So the example which we had done in the lecture, so finding out the response of it, or the circularly convolved output, which is going to be this here, 14, 16, 14, 16, which we had done already in the lecture. This is the same thing we got. So the only you need to know the what is the command circular convolution of x1 comma x2 and n. So this is again 1D we are talking about, and few 2D cases we had discussed. Okay, so now this we can also extend these codes for all the examples which we had done in the lectures for 2D examples, like plotting the shifted impulse sequences and shifted step sequences. So adding them together with the signal operations, multiplying and the shifting operations can be done for the resultant signal can be plotted in this fashion. When 1D signals needs to be plotted, you can straight away use the stem plot and the basic signal models and add them together. Addition, how to do that, and product of them, how to do that we had seen. But when we do the 2D plotting, whatever is dealt in the lectures, that is, to obtain it, you have to plot the stem 3 plot and then rotate it to have a plain kind of 2D version of it. That is n1 and n1 versus n2. What is the amplitude? Those are shown as dots here. But when we plot a stem 3, you would get the view as the 3D plot. Okay, so that is to visualize how the stems, how the amplitude is varying. The third parameter is varying in this fashion. So we had seen the signals, 2D signals and its operations, also the how to plot this, visualize these signals and convolution operation, and how do we do that in the coding, and we would explore further in the next lecture. Thank you.